Basic sigma notation. Let's see what this sigma notation is all about. This would be read as the summation, that's sigma, the summation as I goes from 1 to 4 of AI. Now, it's going to be a sum. We are adding up things. The question is, what are we adding up? Well, first, I is 1. First, I is 1. Then I is 2. And then I is 3. And then I is 4. And what we do is, as we change each I, this changes according to what I is. First, I is 1. So it'll be A1. And then I is 2. So it's A sub 2. And then A sub 3. And then A sub 4. I first equals 1. And then I equals 2. And then I equals 3. And I equals 4. I just need this space down here. Okay. So what if you had this problem? What if you have the summation as I goes from 1 to 3 of 2i plus 1 over 5? How much is this? Well, the rule is write down what's in here exactly the way it is, except change what I is. Change what I is. First I is 1, then I is 2, and then I is finally 3. Remember, it's 2 times I. So it's going to be 2 times 1 plus 1 over 5 plus I is now 2. 2 plus 2 plus 1 over 5 plus I is now 3. 2 times 3 plus 1 over 5. All that changed was I. All of these look exactly the same, except this number keeps changing. What's going on here? I mean, first it's 1, and then it's 2, and then it's 3. Oh, that's what I is. Oh, I is going from 1 to 3. I mean, if you want to calculate this, we can do that too. 2 times 1 is 2, plus 1 is 3. 2 times 2 is 4, plus 1 is 5. Everything's over 5. Plus 2 times 3 is 6, plus 1 is 7 over 5. Everything's over 5. So all we do is we keep the 5 and we add the numerators. 7 plus 3 is 10, plus 5 is 15. So this mess equals to 3. Suppose you have the summation as k goes from 3 to 6 of k squared. So I keep writing that down exactly the way it is, except wherever I see k, I plug in 3, then 4, then 5, all the way up to 6. So it is k squared plus k squared plus k squared plus k squared. K was first 3, and then 4, and then 5, and then 6. So it's 9 plus 16, which is 25. 5 squared is 25. 25 plus 25 is 50. And then when you add on 6 squared, which is 36, you happen to get that the answer is 86. This mess is 86. Let us consider this next problem. The summation as I goes from 1 to 3 of a sub I plus b sub I. So we're just going to write this down exactly the way it is, except wherever we see I, if we see an I, we're going to plug in first 1 and then 2 and then 3. So I is 1. So it's A1 plus B1. Done. Now I is 2. So I write this down exactly the way it looks. I see an A, I see this symbol, I see a B, I also see I. I is now 2. And then I is 3. Now, the order that you add numbers in, that's up to you. Well, I like to add A1 plus A2 plus A3 first. And then whatever that turns out to be, I want to add B1 plus B2 plus B3 to that. B1 plus B2 plus B3 to that. But you know what? 1, 2, 3. This here is nothing more than the summation of A sub I, where I goes from 1 to 3. And what's over here is nothing more than the summation of B sub I as I goes from 1 to 3. What I've shown here is that you can have the distributive law, which we had on the end. Now, if it had been minus BI, it would be A1 minus B1, A2 minus B2, A sub 3 minus B sub 3. And then after adding all the A's, when we add the B's, they're all minus, so I can factor out the minus sign. So if you read the bottom symbol over here, then you have to read the bottom symbol everywhere. And if you're going to read the top symbol, then you have to read the top symbol everywhere. So it's two formulas in one. It distributes. Sigma notation distributes. Now we're going to look at another property of sigma notation. Suppose I goes from 1, I'll make it 4. 4 to 7 of k times A sub I. Well, let's see. First, I is 4, so I get k A sub 4. Then it's 5. And then it's 6. And then finally it's 7. Well, each one of these terms have a factor of k. Can factor it out. Say 4 plus A5 plus A6 plus A7. Now, what's in here is A sub I summation as I goes from 4, 5, 6, 7. I goes from 4 to 7 times the k in front. Now, this is pretty helpful because suppose you have the summation of 3m squared, and say m goes from 4 to 7. So first you have 3 times 4 squared plus 3 times 5 squared plus 3 times 6 squared plus 3 times 7 squared. Well, this is 3 times 16 plus 3 times 25 plus 3 times 36 plus 3 times 7 squared. Now, you can do 1, 2, 3, 4 multiplications. Oh, and 7 squared is 49. We can do 4 multiplications. 4 multiplications. We get 45 plus 75 plus 108 plus, I guess, 147. And then we do 4 additions with bigger numbers. I'll tell you what they're bigger than. We have 48, 75, 105, 147, 15, 20, 25. 6, 10, 17, 3. Or from this line right here, from this equation right here, we could have factored out the 3. 4 squared plus 5 squared plus 6 squared plus 7 squared. We still have to square those numbers to just like I did up here. 16 plus 25 plus 36 plus 49. Now, I'm gonna add 4 numbers. Just like I added 4 numbers up here. My numbers are a little bit smaller, but nonetheless 4 numbers. 15 and 5 is 21. 27. 4, 7, 9, 10, 12. Just trying to think where I made my mistake. Okay, so I understand what's going on here. Let me add this up again, please. So I was going to say that adding up the smaller numbers is easier. Okay, 9 and 6 is 15, 20, 26. 4, 7, 9, 10, 12. So I must have made a mistake adding up these numbers. This is ridiculous. 48, 75, 108, 108, 108, and 147. 15, still not right. 20, 25. Carry the 2. 4, 11, 15, 17. 375. Okay, so now we have it because this was 48, but for whatever reason, I wrote down 45. So it's going to be 3 more. Okay, so finally we get 3 times 126, which is 378. The thing is, I only did 1 multiplication when I went from here to here. I only did 1 multiplication by factoring out the 3. The important thing is the following. Actually, I went down to here. The important thing is the following. Now, whether I did the math right or I did the math wrong, the 3 factors out. And then you have the summation of, now let me not put this bracket. Then you have the summation of this, which is the summation of m squared as m goes from 4 to 7. You can pull out the 3. You can pull out the 3 and it makes life easier. And we showed this up here. Here, a sub I is just m squared. You can pull out the k in front of the sigma notation. Now let us consider this one. Suppose you have the summation of r times a sub I plus s times b sub I. And I is going from 3 to 5. So we get r times a3 plus s times a b3. That's when I is 3. Now I is 4. So we get r times a4 plus s times b4. And now I is 5. We get r times a5. I is 5 plus s times b5. Again, the order I add these 6 numbers in is up to me. I choose to add these 3 first, and then to that I'm going to add SB3 plus SB4 plus SB5. But this here is, well, let's factor out the r. That's r times a3 plus a4 plus a5. And over here, I can factor out the s factor. And then what's in the first bracket is just the summation of a sub I, as I goes from 3 all the way to 5 without missing anything in between, plus s times the summation of b sub I, as I goes from 3, 4, 5, goes from 3 to 5. The big deal is that this becomes this. That is, we can take the summation of the first one, but that r can come out in front. That's what we kind of showed a few problems ago, plus the summation of that. And since s has nothing to do with I, we can factor out the s. Okay, rather than just saying it, I kind of proved it just for this particular problem. I didn't prove it in general. Okay, now let us look at this very classic problem. Suppose you have the summation as I goes from 1 to n of just I. Well, first I is 1, and then it's 2, and then it's 3, all the way up to, say, 2 numbers before n, and then 1 number before n, and then finally n. Well, let's call that sum s. 1 plus 2 plus 3, dot, 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 up to adding up the last 3 numbers. Now, as I said a few times, the order you add numbers in doesn't matter. Well, I want to add these numbers in reverse order. I'm going to do n minus 1, n minus 2, and then down to the last 3 numbers. And we're going to add these 2. S plus s, that's 2s. Now, if I add those 2 first, I'll get n plus 1. Plus, if I add these 2 next, I also get n plus 1. Think about it. You have n marbles in your left hand and 1 marble in your right hand. So you have a total of n plus 1. Well, if you take 1 from your left hand and you put it into your right hand, you're still going to have n plus 1. And then if you take another 1 from your left hand and you put it in your right hand, it's still going to add up to n plus 1. If you take 1 away from that number and you add it to that number, it's still going to be n plus 1. These are all n plus 1s. You have n and you take away 3. Sorry, you take away 2, but then you add 3 back, you're going to have 1 more. N plus 1. You add these, n plus 1. Now, this is repeated addition. And we have a rule for repeated addition. If you so how many times am I adding these? Well, you know what? The top number, we're counting it for us. This was the first n plus 1, and that's a 1. This is the second time we added n plus 1 to itself. That's 2. Look at this. This is the third time we're adding n plus 1 to itself. In fact, we're adding n plus 1 to itself n times. But that's just what multiplication means. So 2s is equal to n times n plus 1. So s, dividing both sides by 2, s must equal that. But what was s? S was this. S was this. Which was that? That is the summation of I, as I goes from 1 to n, is equal to this. So let me write this down more formally. The summation as I goes from 1 to n of I is n times n plus 1 over 2. Now, it wouldn't be fair if I didn't make this statement. Just want to think for a moment. Okay, I'm trying to think if it went from 1 to 50 or 1 to 100. I think it went 1 to 50. There's this very famous mathematician, I think he's German, and his name is Gauss. Gauss was beyond brilliant. And when Gauss was in a very young grade in elementary school, for punishment, the class was talking a lot. So for punishment, the teacher said, I want you all to add up the numbers from 1 to 50 and don't talk until you figure it out. So what Gauss did was, he did exactly what we did above. He realized, this is a grammar school student, 3rd grade maybe. He realized that if he wrote the numbers backwards and he added them, he'd be adding 51 each and every time. So it's going to be 50 times 51, the sum. But that's twice what he wanted. But he divided by 2. But the more I think about it, based on the answer we're getting, I think Professor Gauss, he went up to 100. That is, the teacher said, add up all the numbers from 0 to 100. So we have so he had 98, he had written 99, and 100. And then 100, 99, 98, all the way down to 3, 2, 1. And what Gauss got was 101 plus this sum is 101 plus this is 101 many, many times. In fact, he realized that he had 101 100 times. First time, second time, third time, 98, 99, 100 times. So it's 100 times 101. But then he had to divide by 2. 100 divided by 2 is 50. And Gauss knew that this was 50-50. So if you add up the first 100 numbers, it adds up to 5,050. And to do it the way the teacher wanted them to do, 1 plus 2 is 3, 3 plus 4 is 7, then add 5, etc. That would have taken a while. That would have taken a while. But Gauss was beyond brilliant, and he realized this, and he started to talk. The teacher said, I told you not to talk until you add up the first 50 numbers. And he goes, oh, I did. It's 5,050. And I'm sure the teacher thought he was wrong, but he wasn't. He was brilliant. Okay. And now, again, knowing that the summation of I, as I goes from 1 to n, is equal to n times n plus 1 over 2, what would the summation of I be as I goes from 1 to 5? Well, the formula is based on knowing what n is. Well, n is 5. So I'm just going to write 5 instead of n. It's n, but I'll say n. It's n times n plus 1 over 2. Okay, now I'll say math. 5 times 6 over 2. This is 15. And if you add up the first 5 numbers the more conventional way, you get 5, 9, 10, 13, 15. The formula works. Now, let us now look at another formula. Suppose you have the summation as I goes from 1 to n of just k. So first, I is 1. Oh, that's k. Doesn't care about I. Plus, now I is 2. So that's k. And then I is 3. And then I is 4 and 5. And eventually I is n. And when I is n, this is still k. So how many k's are we adding together? N of them. This is n times k. Now this one we proved because I didn't just do it for n equals 7 or for the upper limit to be 7. It was arbitrary. Now, we have this other formula. The summation is I goes from 1 to n of I squared. This, see if I can remember, it's n times 2n plus 1. Or you know what? Let me not say it that way. It's n times n plus 1 times 2n plus 1, and this is all over 6. You need to know this rule. Now, suppose I ask you what is the summation as I goes from 1 to 4 of I squared. Well, the only difference between this problem here and this over here is that n became 4. N is now 4. Okay, I got it, and it's 4. So I'm going to write down this formula, but instead of n, I'm going to say n, but I'm going to write 4. It's n times n plus 1 times 2 times n plus 1. Oops, I didn't write 4 for n. Over 6. All right. So this is 4. That's 5. And that's 8 plus 1, which is 9. All over 6. Well, 4 times 9 is 36. Divided by 6 is 6. So we end up with 5 times 6, which is 30. Okay, 5 times 6, which is 30. If you don't believe that, we have 1 squared plus 2 squared plus 3 squared plus 4 squared. That's 1 squared, that's 2 squared, that's 3 squared, and that's not 4 squared. So let's fix it. That's 4 squared. That's 25, 29, 30. Got it. Formula works. Okay. So, what if you were asked to find the summation as, let's call it J. J goes from 1 to 100 of J squared. Oh, square. 1 to 100. That just means N is 100 in this formula. So it's N times N plus 1 times 2 times N plus 1 all over 6. It's 100 times 101 times 201 over 6. The sum of these digits in 201 add up to 3. That means that number is divisible by 3. It is 67. And I divide this number by 3, I get 2. Now 2 goes into 2 one time. It goes into that number 50 times. And 50 times 101 is 50/50. I'll leave it to you to multiply it by 67. But that would be that answer. Now, let us now state another formula. The summation of I cubed. So we did the summation of I, the summation of I squared. Now we're doing the summation of I cubed as I goes from 1 to N. This is exactly the same as the summation of just I. But then you have to square everything. That is, it's N squared, N plus 1 squared over 2 squared. So if you were asked what is the summation as I goes from 1 to 5 of I cube is, well, N became 5. So I'm just going to write that formula, but I'm going to write 5 for N. I'm going to say N, but write 5. It's N squared times N plus 1 squared over 4. It's 25 times 36 over 4. 5 plus 1 is 6. 4 goes into 36 9 times. 9 quarters is 225. Now, we can maybe do this. 1 cube plus 2 cube plus 3 cube plus 4 cube plus 5 cube. Well, that's 1 cube. 2 cube is 2 times 2 times 2, which is 8. 3 cubed is 27. Well, 4 times 4 is 16. And if you multiply that by another 4, you'll get 64. And 5 times 5 is 25. You multiply it by another 5, 25, 50, 75, 100, 125. And now we add up these numbers: 1, 8, 27, 64, 125. And we could have done 3 of the problems by now using the formula. 5, 9, 10. Let's hold off on that 10 for a moment. 7 plus 8 is 15, plus the 10 is 25. 2, 4, 10, 12. Look at that. We got 225. So the formula seems to be working. So just want to say that you must know the following. The summation as I goes from 1 to N of I is N times N plus 1 over 2. You should know the summation as I goes from 1 to N of I squared is N times N plus 1 times 2N plus 1 over 6. and that the summation of I cubed as I goes from 1 to n is equal to n squared. It's just that one squared. N squared times n plus 1 squared over 2 squared. And you should also know that the summation as I goes from 1 to n of just the constant is just going to be n times the constant. You need to know these. I could remember them, you can. This one's easily derived, and this one here you could derive easily. The other two, you're probably not ready to derive those formulas yet. You would have to do it by a method you haven't learned yet. Now, suppose you have the summation as I goes from 1 to n of 1 over n cubed times, say, I minus 1 squared. And that's not enough. You want to take the limit as n goes to infinity. Now, before you take the limit of that mess, you need to know what that mess is. So we're not going to take the limit for a while. Okay, this has nothing to do with I, so I can pull it out in front. So it's 1 over n cubed times the summation as I goes from 1 to n of I minus 1 squared. One other comment. The reason I couldn't pull this all the way in front is because the limit is based on n. Okay, so this is equal to the limit as n goes to infinity of 1 over n cubed times the summation. Well, what are we actually summing up? That is, let's square it. Let's square I minus 1. It's going to be I squared minus 2i plus 1. And we learned earlier that sigma notation distributes over addition and subtraction. So it's 1 over n cubed times the summation as I goes from 1 to n of I squared minus the summation as I goes from 1 to n of 2i. I can even factor out the 2 plus the summation of that constant. I goes from 1 to n. Now this is equal to the limit as n goes to infinity of 1 over n cubed. Now this first summation, have to know it is n times n plus 1 times 2n plus 1 over 6 minus 2 times this summation, which is n times n plus 1 over 2. The 2's happen to cancel, plus this third summation, which is n times 1, which is just n. Okay, so let us see what we have going. So when I look what's inside the parentheses, I see that each term, these are the terms. Here it's 1 times n. Each term has a factor of n. I can factor that out. I have the limit as n goes to infinity of n over n cubed. And then I just write down what's inside the big yellow brackets except what's checked. What's checked, I factored out. Okay, oops, this is over 6. So now we need to clean this up a little bit. First, I'll say that that's 1 over n squared. And we need everything to be over 6. So I'm going to multiply this over here by 6 over 6. And 1 is 6 over 6. So now everything is over 6. So let's figure out what the numerators are. Let's distribute, that is, let's multiply this out. You get 2n squared plus n plus another 2n, that's 3n plus 1. Okay, and then we are taking away 6n plus 6. 6n plus 6, and then we are adding 6. All right. In fact, I'll factor out this 6. I can pull it all the way in the front, but I won't bother. So you have 1 over 6n squared. You have 2n squared. 3n minus 6n is minus 3n. Minus 6 plus 6 is 0 plus 1. Okay, so now we are in a position to answer this limit. 1 times that mess, of course, is this mess, over 6n squared. This is equal to 1/3, because the leading coefficients are the same, so you get 2 over 6, or 1/3. Let's try one more of these type problems. Suppose we try to do this problem. What is the limit as n goes to infinity of 1 plus 2i over n all squared times 2 over n and summation. Summation as I goes from 1 to n. Well, the 2 over n here has nothing to do with I. It's a constant with respect to I. So I can pull it out in front of the sigma notation. So basically, we're going to have to figure out what we get when we add this. We need to figure out what that is. Okay. So let's square it. So we have the limit as n goes to infinity of 2 over n times the summation as I goes from 1 to n, and now we have to square what's inside the brackets. Now squaring this is clean. You square the 1 plus, you do 1 times 2i over n times 2. Let's make that a nice n. And then you get 4i over n. And then you square the 2i over n, which will give you 4i squared over n squared. 4i squared over n squared. Okay. Now we start using our formulas. This is the limit as n goes to infinity of 2 over n times, now summation distributes. So let us do that. It's the summation of 1. Summation as I goes from 1 to n of 1 plus the summation of that. But the 4 over n has nothing to do with the I that's changing. But the I is. This I is changing. Plus the summation of I squared, but the 4 over n squared can factor out in front. Now here is where you just have to know your formulas. 2 over n. The summation of 1, that's 1 plus 1 plus 1, n times, that's 1 times n. Plus 4 over n, the summation of I is n times n plus 1 over 2, plus 4 over n squared times the summation of I squared. That's n times n plus 1 times 2n plus 1 all over 6. Let us clean that up. So it's the limit as n goes to infinity of 2 over n times. Well, that's just n. Here, the n's cancel, and 4 over 2 becomes 2. So it's 2 times n plus 1. Okay, over here, the 4 6 becomes 2/3, and 1 n in the top kills off 1 n in the bottom. And that scares me, to be honest. Oh, no it doesn't. Plus 2 times n plus 1 times 2n plus 1 all over 3 times n. Okay, now I'm actually going to put this n here back inside the fraction. So it's the limit, actually, let me clean up what's inside first. You have n plus 2n plus 2 plus n squared, 2n squared times the 2 in front, that's going to be 4n squared, plus n, plus another 2n, that's 3n, times the 2 in front, that's 6n, and then finally 1 times 1 is 1, times the 2 in the front. And all of this is over 3n. Okay. Let us get a common denominator. Oh, let's first combine like we can, what we can. That's 3n plus 2. Now I'm going to multiply this by 3n over 3n. So now we have common denominators. So 4n squared plus 6n plus 2 all over the common denominator. This is equal to the limit as n goes to infinity. I am going to factor out that common denominator, so I'll have 2 over 3n squared. Now, this here is 6n squared plus 6n plus the other numerator. This gives us the limit as n goes to infinity of 2 over 3n squared times 6n squared plus 4n squared, where that's 10n squared, plus 12n plus 2. Now let's see if I can sneak in one more line. This is the limit as n goes to infinity of 2 over 3n squared or 2 times. Now, let me distribute the 2 and then we'll be done. When I distribute that 2, I am going to get 20n squared plus 24n plus 4. So the final answer, since the numerator and denominator have the same degree, the final answer is going to be 20 over 3, which is 6 2/3. That finishes this video for basic sigma notation.